Well, hello everybody, this is Mr. Kinney. I'm going to go over the mole-mole problems on this. So in stoichiometry, when we do conversions, let me back up just a little bit here. When we do conversions, I'm going to put this conversion chart. This is from our objective sheet. Zoom out, Mr. Kinney. All right, so this conversion chart, the mole, and I like to call this the most valuable player, MVP of chemistry. This is just a conversion chart. And the mole helps us convert, in chemistry, volumes of gases to what the mass would be, even to how many particles, number of molecules. So the mole just lets us convert, just like in math and geometry, that the pi helps you convert between radius, circumference, and area, and even volume of a circle. So the mole is just a conversion step that lets us go between stuff that we can actually measure, or in some cases we couldn't actually measure. So up to now we've done this part of the process. We've converted mass into moles, and we've converted moles into mass. Now what we're going to work on in chemical equations. When you have a balanced chemical equation, for example, like down here at the bottom of this one, we've got two magnesiums react with one O2 molecule, and I just put the coefficient 1 in there, and it'll produce two molecules of magnesium oxide. So up to now, we've just learned this as two atoms of magnesium react with one molecule of oxygen gas to produce two molecules of magnesium oxide. We can restate this now to say, if you get 2 moles of magnesium metal and react it with 1 mole of oxygen gas, it will produce 2 moles of magnesium oxide. So that's how in stoichiometry we would read this equation now. And when we do these conversions, these mass-mass, they're going to be a 3-step conversion. You've got the first part, converting grams into moles. Then you've got the middle part, which we're working on this one, the molar ratio, comparing moles of one compound, oxygen gas, to moles of the other one over here. And then, often in stoichiometry, then we're going to continue on to a 3rd step. But today, we're just really focusing right here on this one, because this is the branch between one type of compound, in this case magnesium, and then how much oxygen would be produced. So, when you look at this chart, you can see that when you're going from whatever compound A is to whatever compound B is, follow this arrow. Since we're going over to compound B, we want the moles of compound B, and that's going to be the coefficient in the balanced equation, divided by the moles of where we came from. We came from compound A. So in this problem over here, since this problem we are trying to convert into how many liters of oxygen, we need to put that in the balanced equation, there's 1 mole of oxygen gas, and we came from, in this problem, there was 2 moles of magnesium. So these mole-mole ratios, 1 mole of oxygen gas for every 2 moles of magnesium. This is our molar ratio. And since in the problem we want to find out some information about oxygen, it'll go on the top of the conversion factor. Notice here, if we're going this way to compound B, whatever we're going to always goes on the top of the conversion factor, and where we came from goes down here. So let's get to work on the first problem. So in this problem here, we've got nitrogen. Now this is nitrogen gas. Is going to react with and I'm going to say 1 mole of nitrogen gas. So I'm going to put a coefficient 1 over here. Let me get rid of that 1 there, sorry. So we have 1 mole of nitrogen gas is reacting with 3 moles of hydrogen gas to produce 2 moles of ammonia. And if it's hot, it could be ammonia gas. So that's ammonia. And in this problem, we want to know how many moles of hydrogen are needed to completely react with 2 moles of with 2 moles of nitrogen. So in this problem here, you need to always assign, you got to figure out what's given. And in this problem, the given, what it is we're trying to convert is 2 moles of nitrogen. So this is the given. All right. And we want to find out how many moles of hydrogen we get. So I'm going to put down here mole of, now it's hydrogen gas because in the balanced equation it's H2. So moles of hydrogen, that's what we're looking for. That's what we want to convert to. So in all of our stoichiometric problems and any conversion problem, we start with what's given. We were given 2 moles of nitrogen gas. So that's the given, 2 moles. Let me zoom in here now so it'll be a little bit easier to see. And I'll use my other pen, it's a little pencil, it's a little darker. So we got 2 moles of nitrogen gas. Now we have to put N2 because nitrogen gas exists like that. So that's just our given, like we do in any problem. Now what we want to do is we want to convert it. We want to see if we have 2 moles of this, how many moles of hydrogen gas would we need for this reaction to occur? And to do that, we will multiply it by the molar ratio. So when we take a look at this problem, where there's 3 moles of hydrogen gas for every 1 mole of nitrogen gas. So I'm going to set up this problem. Since I want to get rid of nitrogen gas, moles of nitrogen, we're going to put that there's 1 mole of nitrogen gas, N2, make sure you can see that. And for every 1 mole of nitrogen gas, there's 3 moles of hydrogen gas. Now when we do these mole-mole ratios, we are focused on the coefficients. The coefficients tell us how many moles of each there are. Don't get confused. Don't think, we're not asking that there's 6 hydrogen atoms there. Some people get mixed up and they put a 6 here. No, not in the mole-mole ratio. The mole-mole ratio is going to be the coefficients we have on the balanced equation. And so for every 1 mole of nitrogen, we'll have 3 moles of hydrogen. That cancels like this. And now we've got 2 times 3 is going to equal 6 moles of hydrogen gas. Now, what's kind of, when you step back from these for a moment, take a look, it should make sense. It says for every one of these we have, we're going to need to have 3 of those. So if we're starting with 2 nitrogens, we need 3 times as much, and we would need 6 hydrogens over there. And so this step by step gets us at that answer. As you get through and practice these more, it becomes a little more easy. Now, in the next problem, how many moles of oxygen are produced? Okay, so now we're looking for moles of oxygen. So over here we want to put, we're looking for moles of O2. Always please practice these. Make sure you know what you're looking for. And let's see, how many moles of oxygen are produced by the decomposition of 6 moles of potassium chloride? Okay, so this is our given. This is the given in the problem, meaning this is what we got to convert. So we're going to start, we'll get that set up with 6 moles now of potassium, KClO3. Unfortunately, never mind, I was thinking ahead here. So just like we did over here, we're going to get this set up. You're going to take a look at the mole-mole ratio. And since we're focusing on, there's 2 moles of potassium chlorate for every 3 moles of oxygen. So you get it set up properly so that the moles of potassium chlorate balance out, are proportional to the moles of oxygen, and that'll cancel out for you there. I'm not going to go through the steps here. For number 3, we have zinc. Now I'm going to put the coefficient 1 in front of this. Let me get rid of the 3 so we don't think it's there. 1 mole of zinc reacts with 2 moles of hydrochloric acid, producing 1 mole of zinc chloride plus 1 mole of hydrogen gas. So that's how you'd read that. So in this problem, how many moles of hydrogen are produced? Okay, so we're over here, moles of H2. That's what we're looking for. That's what we want to end up with. From the reaction of 3 moles of zinc, that's the given. Now it goes off and it gives us a little extra thing that we really don't need to worry about. It says in excess hydrochloric acid. Well, that just means we've got plenty of acid for the reaction to occur. Basically, you can ignore this now, okay, because we got plenty. So let's get it set up. 3 moles of zinc is what's given. Now when we first set it up, don't look up here yet. We're just putting what's given as you do in all. 3 moles of zinc. Now you got to look at the balanced equation because we want to set up the mole-mole ratio, and we're comparing zinc to hydrogen gas, and for every zinc atom that we react, we're going to end up with 1 mole of hydrogen gas. So that's going to be our mole-mole ratio, 1 mole of zinc to 1 mole of hydrogen. You get them set in there. Just like we did up there, you get it set up so these two will cancel, and your answer will be here. Now, number 4, this is propane. I'm going to just cross that off. So I'm going to put that there's 1 mole of propane reacts with 5 moles of oxygen gas to produce 3 moles of carbon dioxide and 4 moles of water. And let's see, how many moles of oxygen are necessary? Okay, so that's what we're looking for. Moles of O2 in this problem. And what's given is 4 moles of propane. So we know that we start off with 4 moles of propane. So we're going to put 4 moles. Now propane is C3H8. 4 moles of propane. And when we look now, you look to the balanced equation now, because the mole ratio is what we need to put in. And we know that for every 1 mole of propane, we are going to have 5 we need to have 5 moles of oxygen. So that's our molar ratio, 1 to 5. And since we have moles of propane here, you want to put your 1 mole of propane here, and that'll be for every 5 moles of oxygen. Work it out. Number 5. We got, now these are going to, yeah, okay. How many moles of potassium nitrate are produced? Okay, that's what we're looking for. Moles of KNO3, that's potassium nitrate. And from given is going to be 2 moles of potassium phosphate. So 2 moles of potassium phosphate is our given. So 2 mole. Now, don't get lazy and not write these out like I am. 2 moles of potassium phosphate. You have to do this. I know it's a pain, but if you don't write everything out, you're going to get lost later on when the equations are bigger, when the conversions are bigger. So now we've got our given here, 2 moles of potassium phosphate, and we're looking for potassium nitrate, so we need to focus on this one here. And our problem says if we have 1 mole of potassium phosphate, we will get it'll react with 1 mole of aluminum nitrate to produce 3 moles of potassium nitrate and 1 mole of aluminum phosphate. Well, we're looking for potassium nitrate, so this is the one we're paying attention we want to find, and this is the one that we were given in the problem. So the mole ratio is for every 1 potassium phosphate, we've got 3 potassium nitrates. So there's our ratio, 1 to 3. Now, we don't want to set it up this way, 1 mole of potassium phosphate, because what we'd end up with multiplying potassium phosphate twice. No, you don't want to do that. There's 1 mole K3PO4, and then there's going to be 3 moles of KNO, potassium nitrate. Those will cancel out, and then you've got your answer there. So what we've just done is we've just practiced in our stoichiometric relationships when we can compare 1 compound in a reaction to the other, either another compound that's produced, or if we might be comparing 2 reactants. If we have this much of reactant 1, how many reactants 2 do we need? Anyway, there you go. Enough said. Over and out.